Good afternoon. Thank you very much for coming to my session today. I know it's one of the last sessions of KubeCon. It's Friday. We're all tired and everything, but if you're here, you probably want to know something, or at least you're curious about how we do wildfire prevention with Kubernetes and AI. My name is Andrea Giardini. I'm a CNCF ambassador. I work as an SRE for Overstory, and in my free time, I also organize community events and community conferences around Europe. The title of my talk is Kubernetes and AI to Protect Our Forest, a cloud-native infrastructure for wildfire prevention. Like me, a couple of years ago, before I started working for Overstory, I didn't actually know much about wildfires. Wildfires are events that in Europe are a little bit more rare compared to the US, because of the density, because of the geography of the US territory. But they're events that are extremely destructive for people's lives, community, building, businesses, and so on. These events are often very sudden, they happen unpredictably, and they bring a lot of destruction to our people. Just to give you an idea, just a couple of months ago, I'm sure you're aware, I'm sure you're following the news, a big wildfire spread out in Southern California. This was the second biggest wildfire that happened in California. Over 29 people died, over 200,000 people got evacuated, 18,000 homes destroyed, and over 57,000 acres of land burned down. Just to give you an idea of what 57,000 acres of land means, this is the area that would have burned in London that represents 57,000 acres. And this was not even the largest wildfire that happened in California. The 2018 Camp Fire was spread over an area that was almost 3 times as large, 153,000 acres. Another thing that I didn't know about wildfire is that in California specifically, over 60% of the most destructive wildfires have been caused by defective power lines. I know it sounds curious. I know that we expect, wildfires to be caused by humans most of the time, just a cigarette that is not turned down correctly or things like this. But power lines are actually a big responsible of this kind of wildfire, especially in California. And wildfire prevention is not an easy task for a multitude of reasons. The first one, in respect to power lines, is that the power line infrastructure is very vast. It takes a lot of space, it's very complex, it has a big number of different substations, and the infrastructure is just really, really big to handle and to maintain. And if you think about it, power lines are bringing us electricity 365 days a year. So it's the kind of infrastructure that needs to be, as close as possible as a 100% uptime. The second cause why wildfire prevention is important, but is also difficult at the same time, is that failures are always sudden and catastrophic. You might have heard that just a couple of weeks ago, a power substation near the Heathrow airport failed, and that caused the whole Heathrow airport to be shut down for over 24 hours. Over 1,000 flights got disrupted, over 300,000 passengers got affected. And this was just a small power substation. You see how the impact of this can be sudden and catastrophic and can cause a lot of disruption. Finally, if you think about it, much of this infrastructure, much of these power lines and network are always subject to atmospheric agents. So they can get damaged by all kinds of things, let it be vegetation or a storm, thunders, and so on. Inspecting them, it's also not easy. Very often, those power lines, they cross, for example, private properties. So if we want to go and inspect them visually, we need to ask permission for these people to go in their private property and inspect their power lines. This is extremely time-consuming and extremely costly for power utility companies. And this is why Overstory has started to think in a different approach. What if instead of going and inspecting those power lines visually, what if we do it through satellite images, specifically very high-resolution satellite imagery and machine learning, so that we can get insights from the sky, pretty much, on how our infrastructure is doing, if it needs maintenance, if there is a damaged line, for example. We do that with a simple process. Well, simple. It will be simple because I'm explaining it to you in these 3 different steps, but actually the whole process is a lot more complicated. The idea is, first of all, that we get vegetation data from different sources. Some of those are satellite images, some of those are aerial images. So we have providers that we query, and they give us high-resolution satellite images. Think that the highest resolution that we use is 15 centimeters. Then we combine this data with information that we get from the energy provider. So they give us all the coordinates of the poles, the lines, and the kind of territory where their infrastructure is standing on, and so on. And basically what we do is that we combine these 2 different types of data to create a map, a risk map, so that the utility company can go and see where there is an elevated risk of wildfire. The idea is that whenever the vegetation gets too close to the power lines, there is an elevated risk of wildfire. And in this case, the provider can go and trim the vegetation before a wildfire spreads out. So we make it easy for those utilities to look at the map, to look at our product and the results of our scan, and basically understand where they need to go and act faster in order to prevent the next wildfire. But how are we doing that? And how are we doing that using Kubernetes and cloud-native solutions? Before we move into what we currently have right now, I want to take a step back and think about how we got started. We are a startup. When I joined Overstory, we were around 20 people. Right now, we're over 100. When we got started, we need to break things and move fast. This is, what a lot of people say about startup. We needed to figure out things, right on the ground. So when we started, we actually had a stack that was extremely simple. We just used Kubernetes because it was providing us the right balance between flexibility and stability. You can think that our workload can take anything from 1 CPU and 4 gigs of memory to 72 CPUs and alpha terabyte of memory, and stability. So we had that with Kubernetes. And most of our processing was happening with Jupyter Hub. I'm sure you're familiar already with Jupyter Notebooks. Jupyter Hub is just a tool that allows you to create different Jupyter Notebooks using different types of resources. And in the beginning, that was all we had. We started with this, and everything was a Jupyter Notebook. So we would create all our processing pipelines, we would create all our data analysis in Jupyter Notebook. We built some custom integration to it so that people could go and select the container image that they wanted to spin, select the machine where they wanted to run it, and basically they would have the possibility of running their Jupyter Notebook on a machine which, much higher power compared to their laptop, eventually a bigger GPU or a large amount of memory or CPU. So data scientists could just go on this platform, select the machine that they wanted, select the image that they wanted, and run their experiment in a Jupyter Notebook. As you can imagine, Jupyter Notebooks are great for experimenting, but this became a nightmare pretty early. Repeatability and tracking in particular was extremely difficult. And as we have to repeat these scans over time, every time we had these kind of messages all over Slack. Hey, do you remember which version of Pandas we used a year ago? The new one breaks everything. And the whole process in general was just very manual. It was really, we always needed to assign a data scientist with every delivery that we were doing for a client. And this data scientist would have to go through the Jupyter Notebook step by step, fix the problem that they would encounter on the way, and pretty much deliver the results to the final client. It was a very one-to-one binding. One request from the client, one data scientist assigned to it. So after a while, it was just time to automate and move forward. We set to ourselves 2 main objectives. The first one, getting rid of Jupyter Notebook. We tried different combination of things. We tried using a tool called NBDev that allows you to take your Jupyter Notebook and convert it into a Python package. We were not very successful with that, I have to say. In general, what we experienced that Jupyter Notebook are difficult to maintain, difficult to test, and tracking with Git was very complicated. If you don't know about it, a Jupyter Notebook is pretty much a giant JSON file. So you can imagine what that means whenever you need to track that in Git. And the second, and probably the most important objective, was that we wanted to automate those workflow runs. We wanted to break this relationship between the number of data scientists we have and the number of projects that we were running. So we needed for a data and workflow orchestrator. In here, we stumbled upon a workflow orchestrator called Dagster. This is a project I'm a fan of. I've been contributed to the open source project for quite some time. We started using it since version 0 point something, and now there are like 1.10. I personally like Dagster because, first of all, it's an open source project. It's backed by a company in the US with their own cloud offering, but we've been using their open source version very successfully. It gave us immediately a couple of things that we like. First of all, fast development. If you have experience with data and workflow orchestrator, you know that just understanding what is the right way of setting up your Python project can be a pain. Dagster makes it very easy. Dagster, scaffold, project name, and you get the project structure out of the box with all the best use cases from their maintainers. It was very easy to test locally. It was very easy to get started really, really fast. It all works with Python modules, which our data scientists and data engineers like. And this is something where I'm a little bit biased as a cloud engineer. It's very cloud native. You can really see that people built this tool with cloud native in mind. So what we do at Overstory is that we run Dagster in our Kubernetes cluster. And the setup, if you look at this slide, it's a classical microservice architecture setup. So our user, that you can see on the right side of the slide, accesses the web interface of Dagster, which is called Dagit, as a normal web application. Basically, what they get is an overview of the system, which pipelines are failing, which pipelines are successful, which pipelines need attention. There is another component called the Dagster daemon, which takes care of running the pipelines based on a certain schedule or on certain condition, and monitor pipelines while they're running, so that if there is a step that needs to be retried, it gets retried, and if the pipeline fails, it notifies the final user. And all of these boxes that you see, they are all deployments. All this, they are all stateless applications. And then you can see in the lower part of the slide a set of boxes that I called deployment. Dagster calls them code locations. Basically, each one of those is a gRPC server. It's a gRPC server that exposes, basically advertises to the Dagster daemon and the web interface, which pipelines are present in that code location, which schedules, sensor, assets, and so on. So each one of those deployments is independent, meaning that each team that we have inside of our story is responsible for one of the or more of these code locations. And they can do whatever they want with them. They can create a new pipeline, remove it, edit it, modify it, and so on. And the big advantage here is that whenever a team breaks one of these deployments, all the other deployments are not affected. There is very high isolation between them. And that's extremely important as the company started to grow up. When I said before that Dagster is really something that has been built with cloud native in mind, I wanted to bring you a couple of examples as well. One of the features that I like the most about Dagster, and that's something where I had experience with other tools and had a lot of trouble with other tools, is the idea behind I/O managers. In other tools, whenever you need to build a pipeline that needs to run locally and in the cloud, I always find it a little bit complicated. Very often, you need to put some logic in the code that you write that says, if I'm running in the cloud, I want my data to be saved in S3. If I'm running it locally, I want my data to be saved locally. You don't need to do that with Dagster. Dagster framework does this for you. So you can focus on the logic of your data, of your application, of your workflow in your Python code, and Dagster abstracts all the rest. In this way, the project stays the same, the code stays the same, but simply based on the environment. If Dagster is running in Kubernetes, it will save its output in S3 on Google Cloud Storage. If it's running locally, it will run on your Dagster daemon and save the file locally, which is a really neat feature because it allows us to really, have a clear cut between the data part of things and the implementation part. Another task that Dagster does really well is that in the age of cloud, data has many different forms, right? When we talk about data processing in the past, usually you had a database, a couple of files here and there. The data that you were processing was more or less uniform. But now we live in the cloud, right? Data can be a big query table, can be a PostgreSQL database, or your Snowflake data store, or a file on GCS. Data can have a lot of different formats. And tools, very often, they focus on how data is built, not on how data is connected with each other. It is more and more difficult with other tools to understand what is the relationship between my PostgreSQL database table and my BigQuery table. And that's because the tool focuses on how data is built, not on how it's connected. A really neat concept that Dagster introduced, on top of the usual jobs and pipelines and steps, is the idea behind assets. An asset in Dagster can be anything, can be any data, any type of data. Again, a BigQuery table, it can be an asset. A database can be an asset. A file can be an asset. And what Dagster is very good at is making explicit where the connection between those assets is, which assets depends on each other, and so on. In here, I just put a couple of examples. I pulled them from their documentation. You can see very clearly that there are 2 Airbyte ingestion pipelines that then gets processed with 3 different dbt projects, and finally, I'm running my forecast using Python. Simple, easy to visualize. I know where the data is going. I know how the data depends on each other. Another example here on the right side, ingestion is done using Fivetran. I'm then using dbt to modify the data. And finally, I'm predicting the new order using my TensorFlow model. It's easy to understand how the data flows through the system because we're focusing on how data is related, not on how data is built. As I mentioned, in Dagster, they don't want you to go all in on this approach. It's a kind of opt-in situation. You can even mix them, but you still have all the possibilities of running pipelines, in the traditional way, with jobs, pipelines, steps, and so on. Over time, as we started to get more and more experience with Dagster, we also started to build our own libraries. In particular, we have a internal library that we called Maple. We're a company that cares about trees, so our cluster, libraries, and projects very often have name of trees. In this case in particular, I'm showing you a Maple op. You can think of op as pipeline steps. Think of an op as a step, pretty much. What I'm doing here is adding a decorator and saying, okay, this function is not an actual Python function. This one is a step of my pipeline. And I can customize this step however I want. In this case, I'm specifying that I want this function, this particular step, to run on a node that has a GPU, and it's a high memory node. A node that has at least 32 CPUs available and around 390 gigs of memory. And the last 2 lines are also very important. This is a feature of Kubernetes that is relatively recent, but we use extensively. This is called ephemeral volumes. Basically, they are volumes that can be created dynamically and have the same lifetime as the pod. So as the pod gets created, a volume gets attached to it. It stays connected to the pod for the whole lifetime of the pod. And when the pod gets terminated, the volume also gets deleted. And this is very useful for scratch space. So what I'm specifying in this Maple op is that I also want a scratch space. I want 150 gigabytes of volume that is temporary to the lifetime of the pod. And this is very used, for example, to store temporary files. Right now, this is the situation that we have with Maple. We have plans to improve it because I feel like this is still too Kubernetes specific, like our developers need to know too much about Kubernetes to know about this. So in a new version of Maple, the idea is to hide that even more. As Dagster step can be mapped into different pods, Dagster gives us the possibility of playing with it in different ways, in particular in 2 ways that I find quite interesting. The first one is that we can have a pipeline where we have a single pod and a single node. So I can have a pipeline with multiple steps, but all of them will be run in one node with the same amount of allocated resources. So at the beginning of my pipeline, I can say, well, this whole pipeline is going to take 4 CPUs and 8 gigs of memory. And Dagster will run that on a single pod. So all the steps will be run as part of a single pod. Or I can go the other way around and say, look, instead of having a single pod, let's do it in multiple pods, where every step has a different amount of CPUs and resources. And so, for example, I can have a multiple pods, multiple nodes pipeline, where every step has a different type of requirements. In the example below, the first one takes 4 CPU and 8 gigs of memory. The second one requires a lot more CPU, a lot more GPU, and a lot more memory. And finally, the third one uses ephemeral storage. This allows us to not reserve a GPU for the whole duration of a pipeline, but just for the steps that uses that particular feature. If you have a pipeline that lasts 8 hours, you don't want to reserve a GPU for 8 hours and use it just for one. You want to reserve you want to reserve the GPU just for the hour where you're using it, right? As GPUs are really expensive. What is happening now? So at this point, we already became pretty, Dagster, good users. We were contributing back to the open source project. We were working with it very extensively. We started to build more and more pipelines and more assets into it. But now we wanted to take the next step. One thing we noticed with Dagster, one thing we struggle a little bit with, is observability in particular. The Dagster web interface is very self-explanatory. By opening it, I can get like a gist immediately of how my pipelines are doing and how my system is going. But the problem is that it's very difficult to get aggregate statistics. If I want to know something like what is the failure rate of this pipeline over the past 30 days, that's something very difficult to get. Also, some of the dependencies that we have while we build this process are really difficult to model using Dagster native, using the Dagster model. So what we decided to do is to build a platform on top of it, meaning that Dagster will continue to stay our workflow engine, but the logic on how we trigger those pipelines, the parameters and the configuration will happen externally. So we built an interface to Dagster that talks with the Dagster API and that triggers jobs in a certain order or with certain settings, depending on the delivery that we need to do, depending on the data that we need to analyze. And this is how it looks like. So in the lower part of this image, you can see the usual GKE cluster, and we have Dagster installed in there, and that's all and good. On the top right side, we see what we call the platform, the delivery platform. These are different microservices, starter, router, trigger, and watcher, that are all running in Google Cloud Run. We're also big fans of Google Cloud Run. And all their communication happen using Google PubSub, so a classic messaging queuing system. Basically, what happens is that whenever a new event gets triggered in the starter, the router, the trigger, and the watcher basically keep an eye on their execution in Dagster and make sure to trigger jobs in a certain order and make sure to trigger them with the right setting. So the trigger and the watcher are doing nothing more than interacting with the Dagster API and making sure that the flows happens correctly. And then what we get as an output is the possibility of seeing a delivery end-to-end. This whole process that you see at the beginning, from image acquisition to infrastructure, getting the post online from the customer up to the final delivery, it's something that happens all in our platform. Since the communication happens via PubSub between all these different microservices, we are able to export all those messages to BigQuery. We have OpenTelemetry that exports data as well to Google Cloud Metrics, and then we visualize it using Grafana. Grafana is a great tool. It has multiple different data sources, so we can pull data from BigQuery, we can pull data from Google Cloud Metrics, and display them in one unique dashboard to give full visibility to our team. And this is what it looks like. Our orchestration platform dashboard allows us to see something like this, where for every delivery that we have, we can see step by step how it's going, if there are some steps that need attention, if there are some steps that are failing more than usual, and if some steps need manual intervention. That, unfortunately, still happens sometimes. So how do we connect all the pieces? What are we doing right now, and what is the current state of things? Well, this is a screenshot that I took just a couple of weeks ago. For the first time, we managed to run our first delivery end-to-end, zero touch, in 30 minutes. This was not a new delivery. This was a delivery that we had already done in the past, that we were recomputing and comparing the outputs, just to make sure the outputs were the same. And this was a great result. This was the culmination of almost a year of work, pretty much, building our platform from the ground up. This is a team that is separate from mine, so I'm part of the SRE team. This one is the platform team, but we've worked very closely over the past months to make sure that this project was successful. What's next? Well, The first target is always to deliver results to our customer as hands-off as possible. We want to avoid as much as possible manual intervention. We want to avoid doing these results manually, because whenever that happens, the risk of mistakes gets much, much higher. We also plan on building on newer Dagster features to make the pipeline more reliable to changes. We are using Dagster extensively, but they improve very, very fast. It's a startup. They also need to move fast, right? We would like to break the one step, one node, or one job per node assumption. It would be very nice to have multiple jobs or steps per node. And we are looking into both GKE node pool auto-provisioning, but also Kubernetes dynamic resource allocation, which is something that has been talked about several times this week. And finally, this one is one of the trickiest one, I have to say, avoiding as much as possible under-provisioning or over-provisioning resources. The nature of our work and the data we use is that depending on the input image that we get, the same process can take very different amount of CPUs and memories. And this is very difficult to predict in advance. We would like, first of all, to make the Maple API more straightforward to use, so hide even more details from the users, even more, abstract Kubernetes even more, and definitely work on improvements on monitoring and observability. With all the three of this, we hope we will manage in the future to make our delivery more reliable, our client happier, and hopefully prevent the next big wildfire. Let's put it this way. Thank you very much for the attention. This was my talk. I'm Andrea Giardini, work for Overstory. In case you're interested in what I talked today, in case you're curious to hear more about it, our website is overstory.com. And there is also a career page. We're hiring actively people all over Europe and the US. Thank you very much, folks. Any questions? New Dagster feature. Okay, yeah, Rob. Thank you, Rob. Thank you. Rob asked me about new Dagster feature that we are looking to implement. Dagster has a new feature that has been, well, now it's been released like 6 months ago or something like this, called asset checks. Basically, I talked about asset briefly, but the idea with asset checks is that every time your asset is materialized, so it's refreshed, it will run some checks on your asset to make sure that you're not breaking the API downstream. So if you're building a file with some, let's call it a CSV file, it will make sure, for example, that all the rows are in there, so that you're not breaking all the pipelines that are downstream. This is a feature that we don't actively use. We have coded some logic inside our pipelines, which is because we didn't have the feature yet. But it's something that I feel can greatly improve the reliability of our pipelines. Because sometimes you remove a column to a file just because you think nobody's using it, but you never know how many customers you have, how many users you have that are pulling data from you. So that's one of the features I'm looking forward to. Any other question? Yeah. 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 That's a very good call. So basically the question was, we have Dagster running into our infrastructure, and Dagster already provides certain features like triggers and schedulers and so on that are able to do a lot of this automation for you. And the question was, why did you decide to re-implement all this outside of Dagster using the platform? As you correctly said, the part that you were seeing running in Cloud Run, this is all custom developed. This is a little bit more of a use case for Overstory, let's say, than a wide use case. The problem that we have is that our pipeline takes a really long time, because from image acquisition to final delivery, there can be days, pretty much. And also the decision that we make are difficult to model natively in Dagster. And so at a certain point, we gave it a try to implement that in Dagster, but it was just too complicated and too custom, let's put it this way, to use just Dagster native concept. And this is why we decided to build this system that, as you correctly said, runs outside, runs in Google Cloud Platform, and those components are all customly built, pretty much. I hope it answers your questions. Anyone else? Yeah.
You showed us how to allocate different resources for each task.
Yeah.
Where do we configure that? Is it on the assets configuration or on the code location configuration?
Yeah, good question. So what I've shown you before is that you can allocate different resources depending on the task, or you can define the resource like pipeline-wise. Basically, and the question is, how can I do one or the other? You can do that basically always with decorators, so you just use Python decorators. If you put the decorator on the pipeline, the resources are being allocated for the whole pipeline. If you put the decorator step by step, if you select these resources step by step, then each step will have its own resources. That's the idea. Yeah, with code location, you can define some defaults so that you make sure that you always have at least a minimum amount of resources that are allocated to every step. But yeah, you can customize it always using decorators, which I find it really nice because you have everything in code. You don't have to, you're not doing anything manual, any point and click. Yeah. Yeah, yeah, that's true. It's a new feature of Dagster I haven't talked about. It's called Dagster Pipes. I don't have a lot of experience with it, I have to say, but it's also one of the new features that we want to look into because it looks really promising. Okay, thank you very much for the talk. I will be around in case you have any other question. Thank you very much.